Welcome to this sixth lecture of this lecture series. That today we will see the insertion loss based microwave filter design. Now, already we have seen the motivation for going for this design in the previous lecture. Now, today let me first define what is insertion loss. Insertion loss is, its symbol is PLR, and this is the ratio of power available from source to power delivered to load by any subsystem. Suppose I have any subsystem, in this particular case it will be filter, but insertion loss is a generalized concept, that is why let me call it a electronic network. It is a black box, it is a 2-port black box. Now, this side it will be connected maybe to some other block, but for this network this is the source side. So, it will be connected with this source. Similarly, it may be connected to some other block, but to this 2-port network, that is the load. So, it will be connected to another box which is called load. Now, let the power source is delivering P in and the load is taking PL. So, insertion loss, power available from source. What is the power available from the source to this electronic network? That is P in. So, I can write this as P in, and power delivered to load is PL. Obviously, you know that I do not know the impedance level of this, I do not know the impedance level of this. So, and I am assuming that in general this is, there will be some loss here also, but in this particular case, particularly our filter case. So, this filter case is, there is no inside, there is no power dissipation, because we will use only the reactive components, and so the power is not dissipated inside. So, it is a lossless part here internally, but you know that due to this impedance mismatch there can be reflections here. So, the wave is going and then the wave can come back. So, there are reflections. So, all the power may not go here. So, obviously, the power that is reflected, that will go back here. So, here it will be something less power. Similarly, here also due to the impedance mismatch, the wave is going like this, but there may be reflections. So, can I say that all this P N P L. So, the overall reflection coefficient. So, can I say that this is equal to 1 minus gamma, which is a function of omega. This gamma is the reflection coefficient, overall reflection coefficient, which comprises of reflection here, reflection coefficient here and reflection coefficient here. So, by that I can define an overall reflection coefficient between this, and that is gamma, it is a function of omega, and I know that the this ratio will be nothing but 1 minus this, that means 1 minus reflected power. These gammas, please remember, we have earlier discussed that this gamma is a voltage reflection coefficient, that is why we are taking the square thing, because we are talking of power. Now, if there is no mismatch here, that means already impedance matching has taken place between source and this our filter network, and also between load and our filter network, they need to be like this. So, there won't be this reflection coefficient is 0 there, but remember there is one more thing here, that is that this network, whatever power I gave, yesterday also I said that depending on the propagation constant, in the pass band it will flow, but in general a portion of that will go here. In high frequency or microwave, what is that? Suppose I give some voltage, how much voltage comes here, that I can express by a ratio called S parameter S21, S21. So, I can say that under matched condition. So, this is one, and also I should then say that this is S21 square. This S21 is, this is the port 2 of the electronic network, this is port 1. So, actually insertion loss is 1 by this into S21 square. So, under matched condition, both source and load matched, then PLR is nothing but S21 square. Now, here is a pitfall in measurements. Many times I see that in Indian engineers, they say that what is insertion loss? It is S21 square. Please remember that if you have enforced the matching, then only it is true. Otherwise, you should also consider the reflection taking place both here and here. Many times when the measurement takes place, this impedance mismatch is not taken care, and people forget to incorporate this part, the reflection coefficient part. Okay. So, now I can say that I have defined insertion loss. That means, physically what it is? It says that if this network was not there, some power was flowing to the load. If I include this in the circuit, the power will change. So, this difference is basically the insertion loss. So, due to the insertion of this particular electronic network, how much loss I am getting in the circuit. So, in general, this insertion loss IL, this is expressed in dB. So, please remember that 10 log 10 PLR is the insertion loss in dB. Now, here I will take a property of any microwave network. You may not be familiar with this. In graduate level we do not teach that, but in postgraduate the microwave technology courses, there we prove one point, that gamma omega for any two port network, that should be always an even function of omega. So, what does that mean? That means always this is a property, you believe me, or if you want to see, this is proved in any microwave engineering course. So, in any book, particularly our recommended book, this book Microwave Engineering by David Pozar, it is already recommended in your course. So, in this book this is derived, that always gamma is an even function of omega. That means, gamma omega is equal to gamma of minus omega. We will utilize this property. Now, let me write what is gamma omega. Gamma omega is the impedance of the network if either this side or this side looking at. So, input impedance or output impedance here minus the Z naught by Z naught plus. So, if the characteristic impedance of this filter section is Z naught, then source, then this Z omega is the source impedance. If I am talking of this reflection, then this Z omega is the load impedance. And here also there is another property that any impedance, source, load, etc., or the input impedance, there the Z omega can be written as R omega plus J x omega, the resistive part of the impedance and the reactive part of the impedance, and R omega is always again is even function of omega, and x omega is odd function of omega. These properties are also true, as I said that gamma omega is even function. Similarly, this is also true. So, we will write that this will break into that R omega minus Z naught plus J x omega and R omega plus Z naught plus J x omega. Now, what is gamma of minus omega? Because I want to test what is the nature of this PLR. So, we are going there, that this insertion loss has some specific functional characteristic with respect to omega. So, that we are trying to see. So, let me see what is this. This is utilizing these properties, that R omega minus Z omega minus J x omega by R omega plus Z omega minus J x omega. But we know that these two should be equal. So, if I say that, then basically what is this? This right side can be also written as the complex conjugate of gamma omega. You see that this is real. So, this minus this by this minus this. So, we saw that minus gamma minus omega is nothing but gamma conjugate omega. If we have this, so we can say that what happens to this term gamma omega square, because this is there in the insertion loss expression. So, gamma omega square is gamma omega into gamma this is equal to gamma omega is equal to gamma minus omega. This is by definition, and then we have just seen that this is nothing but gamma minus omega. So, I can write it as gamma minus omega whole square, because I can replace this with, or I can write like this, gamma of minus omega and gamma of minus omega. So, that is gamma minus omega whole square. So, I can say, you see the property that gamma omega whole square, can I say, is an even function of omega. So, what does that mean? That gamma omega square, when I will synthesize, as I said from the start, that actually in this insertion loss based method, we specify the insertion loss. We specify the insertion loss, which is nothing but attenuation part, that how it will go in pass band, stop band, etc. For that we require to have these, but this says that these can be of the type even function of omega means all odd function components, odd components are 0. That means, it can have only this a plus b omega square plus c omega 4 plus d omega 6 etcetera. No omega 1, omega 3 like that terms. So, we can say that this gamma omega square can be represented by two polynomials where m and n are real polynomials in omega square. M and n are real polynomial. You see, this is reflection coefficient. So, obviously, this will be m omega square plus n omega square, because it is this plus something. So, what is then PLR? PLR is 1 by 1 minus m omega square by m omega square plus n omega square, and that is 1 plus m omega square by n omega square. So, it says that you can specify anything, but I will be able to realize a filter only if this insertion loss is specified in this given form. That means, if you specify something with omega etcetera, then it will not be realizable. Now, based on this specification, there are various choices. So, already I ask the students to refer to another NPTEL course, Basic Building Blocks of Microwave Engineering, lecture 9, Basic Building Blocks, basic tools, basic tools of microwave engineering, my course. There in lecture 9, actually that was in respect to impedance matching, and there we have seen in details the properties of various polynomials which are used for synthesis. That time it was impedance transformers, but those are also valid for filters. So, please brush up your knowledge of those basic polynomial functions like Butterworth polynomial, Chebyshev polynomial, elliptic polynomial, maximally flat, which is nothing but Butterworth, etcetera, etcetera. So, here we start with the Butterworth polynomial. So, if insertion loss is specified in the form of Butterworth polynomial, you know Butterworth is also called maximally flat, because given the order compared to any other polynomial function, it has, suppose if it is order n, so up to n derivatives are all 0. So, that is why it is called maximally flat response. So, Butterworth polynomial. So, this is the flattest possible pass band. So, that means, if we specify the insertion loss in the pass band by Butterworth filter, then we can say that we will get a very flat response which is desirable in the pass band. Obviously, always 0 cannot be achieved, that attenuation constant 0, but we will achieve a very flat pass band, and by specifying a label we can say that okay, my pass band is, I am not attenuating this all the frequency components in these bands, not more than this amount. So, for a low pass filter, the specification, so low pass filter, the specification is, if we follow Butterworth, you know Butterworth polynomial is given like this. So, already omega square it is a function, you see that it is a function of only omega square. So, it is realizable from this property of m and n, that okay, I can realize it. So, let us try to realize this, and here n is the order of the filter, that you know, sorry, I can make it capital N. So, n is the order of the filter, omega c is the cutoff frequency, low pass filter cutoff frequency will be low pass filter angular cutoff frequency is given by omega c. Now, pass band, if you see this, that pass band extends from pass band omega is equal to 0 to omega is equal to c, and at the band edge, that means suppose I am plotting omega and PLR, then 0, this is omega c. Now, from here it will be having some stop band. So, PLR will change, but what is the PLR at this point, that I can find from here. So, at omega is equal to omega c, PLR is 1 plus k square. So, I can specify now, you know Butterworth response, since we have taken like this, Butterworth response is like this, it is maximally flat, very flat, but in pass band I will have some attenuation, but this is the maximally flat one, but I should know that what is the maximum attenuation I am having. So, this value is what, 1 plus k square. So, suppose I want that okay, no more than 3 dB attenuation or no more than 0.1 dB attenuation. So, I will put that at, I know that at omega is equal to omega c, at cutoff in the pass band the maximum attenuation takes place here in the for Butterworth polynomial, and that value is k square. From that I can always find k. So, for example, if we choose that this our insertion loss maximum value is the PLR maximum at pass band, I won't tolerate more than 3 dB. So, if this is 3 dB, what happens to k, that means this 1 plus k square, 10 log of this is 3. So, from that you can find out k is equal to 1 under this condition. So, we can plot this PLR versus omega by omega c normalized with respect to omega c. So, I know the values will be like this 0.5, 1, 1.5 etcetera. So, this is the point where cutoff will take place, and so what is the value at 0? Let us also see the at 0 what is PLR, this is 1. So, PLR is 1 here, and PLR this value is 1 plus k square. Also, what happens to this polynomial when omega is well into the stop band, that means omega by omega c is a large number. Then can I say that for omega greater than omega c, I can say PLR is approximately k square omega by omega c whole to the power 2n. So, what is the rate of increase of PLR in the stop band. From this I can say that rate of increase of PLR is how much? It is 20 n dB per decade. This is well known. If you have this expression, you can always say this. So, we see that here attenuation, that means alpha increases monotonically with frequency, but we know that it is at lower side of the pass band, it is not much, but at band edge, that means near cutoff, it is increasing, but I can always specify that where it will be level fixed clamp, and this rate of increase is 20 n dB per decade. So, how much you want to achieve this rate? So, that basically by that you select what is the order of the filter. Order means you will have to find how many sections you need to put. Okay. So, third order, fourth order means you will have this. Now, let us go to the another design, that instead of this, if I say that in the low pass filter, unlike this Chebyshev, okay, I want this rate to increase further, that I want it to be sharper than this. I do not mind, obviously you cannot choose everything. So, I will say I want a very sharp rise compared to Butterworth here. I do not mind if instead of monotonically increasing the in pass band, the insertion loss ripples, that means I can have high low, but do not cross this limit. So, that is possible. Chebyshev is the sharpest one, or much sharper than our Butterworth. So, I have this PLR omega by omega c. Let me fix my 1 plus k square. This is designer will choose, and this is my omega c. So, a Butterworth polynomial, it can be. So, first let me draw the maximally flat one. This is my Butterworth maximally flat or Butterworth. Now, this is Chebyshev. Chebyshev has various, depending on the order, the Chebyshev various, but it ripples, whether there will be one ripple, one cycle or two cycle or three cycle, that depends on order. But you see always they are confined between this and this. But so, what is the advantage? You see that here it was monotonically increasing, here I have ripple, but I can specify that okay, be within this limit. So, in pass band it is never crossing this limit. Once it is going away from pass band, it is much sharper than Butterworth, that is its advantage. So, if you want, your prime concern is after pass band, when I entering stop band, I will have a very good cutoff and very sharp cutoff, you opt for this Chebyshev polynomial. So, again you can determine the ripple level by this k square, and what is this rate of increase? If we see the, so in this case, first let me write down the Chebyshev polynomial form 1 plus k square T n square omega by omega c. Now, T n is the Chebyshev polynomial of order n, and we choose like this. So, for large n, again I can say that when omega is greater than omega c, PLR is k square T n square omega by omega c. Now, at high value of omega by omega c, T n, the Chebyshev polynomial, it is approximated, very good approximation is this. So, this becomes k square T n k square into half 2x whole to the power n. So, this is k square by 4 to, this is T n x. So, here I will write 2 omega by omega c. So, 2 omega by omega c whole to the power n. This is T n x. So, T n x square. So, k square by 4 this. So, here you now tell that what is the slope. I have came here because I wanted a sharper slope. So, slope is 20 dB per decade, 20 n dB. So, same as Butterworth. Then you can say that how I am getting it, that what is the advantage. But advantage is that always this value of T n, it is always 2 to the power 2 n by 4 times insertion loss of any Chebyshev filter is 2 to the power 2 n by 4 times larger than Butterworth. Now, obviously, if you go for n is equal to 1, that means a single section Chebyshev, then you do not have any advantage. But the moment you go for n is equal to 2 or n is equal to 3, etc. So, n is equal to 2 means you have 2 to the power 4, 16 by 4, that means 4 times larger than Butterworth, always you will have the value. So, even if the slope are not much different, but you are getting more value of insertion loss. So, your alpha is increased. Then we will see there is another filter called, another very popular filter, particularly in CD-ROM, etc. This is used, this is called elliptic filter. Now, if you want, you have seen that Butterworth and Chebyshev both give same rate of rise, but elliptic is the maximum rate of rise it can give, but what it will, you will suffer that it has ripples both in pass band and stop band. So, Chebyshev you see it monotonically increases once it is in the pass band, it has ripple in once it is attends in the stop band. Here it is in pass band it has ripple, but here it does not have any ripple. Elliptic has ripples in both. So, that means here it will be something like this, how many, that depends on the order. So, it goes and then here again it has ripples, but no problem if you specify that okay, at least everywhere I want this attenuation in the stop band. This is your stop band, this is your pass band. So, here as before you can specify that okay, in pass band it is beyond this and stop band attenuation should be like this, then you go for elliptic. And there is another one, sometimes in a filters, if you have, if your baseband signal or if you want to process the signal, any baseband signal is not a single tone, it has a spread of frequency. Suppose when I am talking up to 20 kilohertz. or roughly from 4 kilohertz to 20 kilohertz, there will be the voice, sorry, 20 hertz to 20 kilohertz. So, you see these different frequencies, if they are attenuated differently, then there will be problem in the reconstruction. So, sometimes that means a linear system I want, filter should also act as a linear system. Sometimes if I can tolerate that, that is not a problem, but in some applications I cannot tolerate that. That time I want that linear phase filter, sorry, this is linear phase filter. So, linear phase means what? That my phase should be specified like this, 1 plus p omega by omega c all to the power 2n. So, if we specify that p is a constant, but I should have this type of variation. So, this is a, as you can guess, that in phase I am specifying a Butterworth type polynomial. This is nothing but a Butterworth type polynomial. So, this is the phase of the voltage transfer function of the filter that should satisfy this. Under this condition, the group delay, because that is a measure of whether I can tolerate or not. As a group, when the baseband signal is moving, so baseband signal or any RF signal with a frequency spread, that what is the group delay, that means what is the maximum what is the delay between the maximum phasing delay and the minimum phasing delay. So, that is given by d phi by d omega, and you see it turns out to be 1 plus p 2n plus 1 omega by omega c whole to the power 2n. So, this is a, again you see it is a maximally flat response. So, that may be tolerable. So, if you use a linear phase filter, you have the like that. There can be other specifications, other polynomials. Still this research is going on, people are using various newer functions from mathematics, they are taking new functions and implementing that to get a more desired attenuation characteristic, etc. So, we have seen that how to do it, but now we will try to see how a microwave engineer will implement this, because this mathematics or this specification is one thing, but finally as an engineer we should implement that. For that we need to have some mechanism. There is nothing fundamentally new, this is all about filters, but unless and until we engineers learn how to design, how to implement it, we do not consider our job finished. Scientists up to this they stop, but we engineers always go on and try to make that, okay, if I want to make it and test it, I should know that after this what will happen. That we will see in the next class, the implementation of these filters. Thank you.